Welcome. This is a lesson on integrals involving logarithmic functions. Logarithmic functions are used all the time in a lot of science and engineering applications. And remember that integrals actually give you the area under the curve. In a previous lesson, we talked about the derivative of natural log of x. We know that the derivative d dx of ln of x is actually equal to 1 over x. Now the thing about derivatives and integrals is you need to remember that they're inverse operations. So if the derivative of natural log of x equals 1 over x, then we actually already know that the integral of 1 over x should actually be ln of x. Okay? So this is what we already know, but because derivatives and integrals are basically just the same thing in reverse, the integral of 1 over x dx is basically just going the other direction. So you start on the right side and move to the left side, and that actually gives you ln of x. But if it's an indefinite integral, if it doesn't have numbers here, it's going to give you ln of x plus c, where c is a constant, just like in calculus 1. Okay? And the only thing that's a little bit strange about this is when you're doing the integral, you actually have to put an absolute value around x. So it's actually going to be ln of absolute value of x plus c. Now the reason you have to put an absolute value around x is because, remember, you can't take the logarithm of a negative number, and absolute value is always positive. So as long as the absolute value is positive, we're never going to be taking the logarithm of a negative number, so we're good. Okay? So the integral of 1 over x equals ln of absolute value of x plus c. But notice, it's just the same formula, but in reverse. The only difference is now we have an absolute value, and the absolute value is there because, once again, x can't be negative. You can't have the inside of a logarithm be negative because the logarithm isn't defined for negative numbers. So, absolute value because inside of logarithm, here it's a natural logarithm, can't be negative. Okay. Alright, so we're going to be mostly working with this formula right here for the next few examples. Okay, we're going to start with a relatively straightforward problem and work our way to some of the harder ones. So example, evaluate each integral. Evaluate each integral. Okay, and for our first example, we're going to be evaluating a relatively easy integral. This one is going to be the integral of dx over x, okay, from negative 7 to negative 3. The integral of dx over x from negative 7 to negative 3. So hopefully you remember this from calculus 1, but this is a definite integral, which means you integrate first and then you plug in the numbers at the end. So what we're going to be using is our new formula up here. The integral of 1 over x dx, that's the same as the integral of dx over x. Means exactly the same thing, right? Because you can just bring the dx out front. So this is the same as the integral of 1 over x dx. from -7 to -3. Now, because this is a definite integral with numbers, that means we're not going to write plus c. This one up here was an indefinite integral, so we wrote a plus c. Notice this one didn't have numbers on the top and the bottom of the integral symbol. Okay? So we should know from that formula up there that the integral of 1 over x is just ln of absolute value of x. Okay, so this is going to be ln of absolute value of x. But because it's a definite integral, we don't write plus c. So for definite integrals, this is calculus 1 stuff, but it's still important that we review it. So this is a definite integral. You plug in numbers at the end. Instead of writing plus c. Plug in the numbers at the end instead of writing plus c. Okay, whereas this one up here, the formula that I gave you, this one is an indefinite integral. So for this one, how do I know it's indefinite? Well, there's no numbers here that we're plugging in. So if there's no numbers on the top and the bottom of the integral, it's indefinite. So we write plus c. Okay, so indefinite integral. And for an indefinite integral, when there's no numbers, you write plus c at the end. And remember, plus c just means plus a constant, because when you take the derivative of a constant, it gives you 0. So there has to be a constant there when you're taking the integral, because otherwise, when you're taking the derivative to go backwards, remember they're inverse operations. If you take the derivative and go backwards, you can take the derivative of c, where c is any constant, and it'll still give you 1 over x, because c will become 0. Okay, but that's calculus 1 stuff, so if you need to go over that, you should review that. But this one's a definite integral, so we plug in numbers at the end instead of writing plus c. So we're going to be doing ln of absolute value of x. Okay, and we're going to be evaluating that from x equals -7 to x equals -3. Now, how do you plug in the numbers when it's a definite integral like this? Well, you plug in the top number first, in for x, and then you subtract the function evaluated at the bottom number. Okay? So this one is going to give us ln of absolute value of -3 minus ln of absolute value of -7. Okay, so first you plug in the top number into the function, and then you subtract the function evaluated at the bottom number. And that's that definite integral business. That's the fundamental theorem of calculus part 2. Is the fancy name for it, but all we really have to do is plug in the numbers. Okay? All right, and then here you can see why we have absolute values. So the reason we have absolute values is, as we can see here, if we didn't have the absolute value, we would have ln of -3, which is undefined. Logarithms are only defined for 0 and positive numbers. They're not defined for negative numbers. But this absolute value changes the sign of negative numbers and makes them positive. Okay, so absolute value is always positive. And that's why they write that absolute value in the formula, in the integral formula, because otherwise we would get undefined here. Okay, so absolute value of -3 is going to be +3. Okay, so we're going to have ln of +3, and then ln of absolute value of -7. Once again, that's going to become +7. So we're going to have ln of 3 minus ln of 7. Okay? And believe it or not, they want you to simplify this a little bit more using a property of logarithms. So if you're adding logarithms, that's the same as multiplying on the inside. But if you're subtracting logarithms, that's the same as dividing on the inside. Okay? So subtracting outside of a logarithm. This is stuff from pre-calculus. Hopefully some of you, at least it rings a bell, even if you don't completely remember it. Okay, so subtracting outside of a logarithm. Subtracting outside of a logarithm is the same as dividing inside. Okay, and that's usually called the quotient rule for logarithms from pre-calculus. I don't know if you remember that. And the order does matter. The order is left to right, top to bottom. So in other words, this is going to become, since we're subtracting outside the logarithm, that's the same as dividing inside the logarithm. And going from left to right and top to bottom, we're going to have ln of 3 over 7. Okay, ln of 3 over 7. And that's actually how they want you to write your answer. So at the end, if you can combine logarithms like that, they do want you to do that. Okay. All right, so that's our first example. That one was a definite integral. So hopefully that one's not too hard. So for the next problem, I want to do an indefinite integral. And this one's a little bit trickier. Okay, this one has a little bit more to it. So for problem number 2, we're going to do the integral of 8y to the 7th dy, integral of 8y to the 7th dy, all over y to the 8 minus 6. The integral of 8y to the 7th dy, all over y to the 8 minus 6. All over y to the 8 minus 6. So with this one, we're going to have to do something more complicated. We're going to have to use u substitution. Now, how do I know we have to use u substitution? Well, the way it's written, it's not in the form of, integral of 1 over x. It's not in that form. So what we're going to do is we're going to actually use u substitution. And when you're using u substitution, you want to choose u, the letter u, to be the inside of a composite function. Okay? So here we use u substitution, a calculus 1 technique, substitution. Substitution. Okay, so it's a calculus 1 technique, and basically you always choose u to be the inside of a composite function. Okay, so choose u to be the inside of a composite function. And remember, a composite function is a function within another function. And that's generally the strategy you use for u substitution. So like here, the composite function is actually going to be 1 over y to the 8 minus 6. So the inside of that composite function is going to be y to the 8 minus 6. Okay, so here, y to the 8 minus 6 is actually going to be our u. Okay. So how does u substitution work? Well, you choose what u is first. So here we know that u equals y to the 8 minus 6. U equals y to the 8 minus 6. Okay, and then what you do next is you take the derivative. Okay, and here it's going to be du dy. Okay, so du dy. gives us, well, using the power rule, we go ahead and bring the exponent out front, and we decrease the exponent by 1. Okay, so we bring this exponent out front, and we decrease the exponent by 1. So that gives us 8y to the 7th. Whereas the derivative of negative 6 is 0 because negative 6 is a constant. So that means du dy equals 8y to the 7th. All right, and then what do we do next? Well, there's a couple of ways of doing it. One way is to isolate du and then try to plug in. But most people find that confusing. So the way I usually teach it is a little bit different. So what I do is I actually isolate dy, okay, and then I plug that in up here. Okay. So for the du dy, I'm actually going to isolate dy. So if I multiply both sides by dy and I divide both sides by 8y to the 7th, that will give me what I need. Okay, so I'm going to get du over 8y to the 7th equals dy. So all I did in that step was I isolated dy. So I multiplied both sides by dy and I divided both sides by 8y to the 7th. Now the reason I usually teach it this way is it can be somewhat easier, because what you do is, since we have dy isolated now, we can actually plug this whole thing in for dy over here in the integral. Okay, so what we've got here is this whole thing can be plugged in for dy. So we have du over 8y to the 7th, and we're plugging that in for dy. Okay, so what's that going to give us? Well, I think I'm actually going to erase this real quick so that I have room to write. Okay, so what we're doing here is we've got the integral of 8y to the 7th over y to the 8 minus 6 times dy, but we just said that dy is actually du over 8y to the 7th. So I plug that in. And we know something else here. We also know that u is actually y to the 8 minus 6. Okay? So instead of writing y to the 8 minus 6 down here on the bottom left, we're going to replace that y to the 8th minus 6 with u. Okay, so we have a u over here on the bottom left. Okay, and then the nice thing about my way is it's a little bit mindless, because you just plug in, for the dy, we plugged in du over 8y to the 7th, and now stuff cancels out. Okay. All right, so what's going to cancel out here is the 8y to the 7th. Those are going to cancel out. So now we're just going to have the integral of 1 over u du. Okay, the integral of 1 over u du. And remember, the integral we learned was in terms of x, but this one is in terms of u, and it has the same layout as the formula that we learned up here. So instead of integral of 1 over x dx, we have the integral of 1 over u du. But the only difference between those formulas is we're replacing each x with the letter u. So on the right side, instead of having ln of absolute value of x, we're going to have ln of absolute value of u plus c. Okay? So same exact formula, we just have a different letter. Okay? So that's what we're going to be using down here. So the integral of 1 over u du is going to give us ln of absolute value of u plus c. Okay, ln of absolute value of u plus c. Now, why did I write plus c? This one is an indefinite integral. Remember, it's an indefinite integral if they don't give you numbers on the top and the bottom of the integral symbol. And for indefinite integrals, you always write plus c at the end. You don't have to plug in any numbers. However, because we did u substitution, we have to plug back in the expression for u. So remember, the original problem was in terms of y, so that means our answer also has to be in terms of y. Okay, so plugging back in, we know that u is actually y to the 8 minus 6, so we're going to plug that in down here. Okay, so instead of ln of absolute value of u, we're going to have ln of absolute value of y to the 8 minus 6 plus c. ln of absolute value of y to the 8 minus 6 plus c. Okay, and that's the whole problem. Because we got it in terms of the original variable, so we're good there. So that's number 2. Okay, and I'm just going to do a few more examples. Okay, so that was number 2. Let's take a look at number 3. Okay, so example number 3 actually has trigonometric functions. But those are pretty easy if you just remember the formulas for them. Okay, so the integral, this one is the integral from 0 to pi over 5. The integral from 0 to pi over 5 of 5 sine of 5t, 5 sine of 5t, all over 4 minus cosine of 5t. And then this entire integral has a dt in front of it. Okay, so the integral from 0 to pi over 5 of 5 sine of 5t all over 4 minus cosine of 5t dt. So because they gave us numbers here, 0 and pi over 5, this one is going to be a definite integral, which means at the end of the problem, after we've integrated it, we're going to be plugging in these numbers. And remember, these numbers are actually in terms of t. Okay, so this is going from t equals 0 to t equals pi over 5. Now this one again is complicated because we can't just use the new formula that we learned right off the bat. So when you have something complicated, usually you end up using u substitution. And you want to make u be the inside of a composite function. And you usually want to choose u to be the inside of the most complicated composite function. So here the most complicated composite function is actually 1 over 4 minus cosine of 5t. So on this one, once again, we're going to do u substitution, and we're going to choose u to be this big denominator here. So that's going to be u. So generally, when you're choosing your u for u substitution, you want to choose the inside of a complicated composite function. Because the problems are generally set up that way, and everything ends up working out. Okay, so here u, we know, is going to equal 4 minus cosine of 5t. Okay, and then du dt, why is it du dt this time? Well, on the last problem, our independent variable was actually y, so we did du dy. But for this one, our independent variable, the variable that the integral is in terms of, is t. So this time the derivative is going to be du dt. Okay, so we have du dt equals, well, the derivative of a constant is 0, so this goes to 0. And then what's the derivative of negative cosine of 5t? Well, right off the bat, we need to review a formula. So the formula is for the derivative of cosine. Okay, so recall, this is from Calculus 1. Recall that ddu of cosine of u is actually equal to negative sine of u. Okay, so negative sine of u times u prime. Okay, so the derivative of cosine is negative sine. And then you have to use the chain rule, so it's also times the derivative of the inside. So that's the formula we need here. So the derivative of cosine of 5t is going to be negative sine of 5t times 5. But there's a minus in front. So we're actually going to have negative of, well, the derivative of cosine is negative sine of 5t. Okay, and the reason there's two minuses is, well, there was already a minus here, and then the derivative of cosine is negative sine. So that gave us two minuses. The one we started with and then the one that we put in there. And then we have to multiply this times u prime. So we have to multiply this times the derivative of 5t. What's the derivative of 5t? Well, the t goes away and we just get a 5. So we're going to get negative sine of 5t times 5. Okay? And then of course we still have this minus out front. So these two minuses are going to cancel out. Okay, and make a plus. So we're going to have du dt. Du dt equals 5 sine of 5t. Now I'm going to teach the way I usually do, which people usually find the easiest way, which is in the last problem, because the variable was y, we isolated dy. In this problem, because the variable is t, we're going to isolate dt. Okay, so isolate dt. On the last one, we isolated dy. Okay, so to isolate dt here, we're going to multiply both sides by dt and divide both sides by 5 sine of 5t. Okay, so we're going to get du over 5 sine of 5t is equal to dt. This is just the way I teach it. Some people, when they're doing u substitution, they move the dt over here, and then they try to play games by plugging things in. But I find that that confuses students, so I prefer teaching it with my method, which is to isolate, well, in this case it's dt. On the last problem, it was dy. When we were doing the u substitution, oh, I erased it. Oh, no, I didn't. Oh, okay, here it is. So in the last problem, we actually isolated dy because y was the variable. And on this one, we isolated dt because t was the variable. Okay, and then the nice thing about my method is you can actually plug in this whole thing, du over 5 sine of 5t. You plug that in for dt up in the integral. Okay, so let me zoom out so we can actually see this. So we're going to be replacing this dt up here with du over 5 sine of 5t. Okay? And of course, this 4 minus cosine of 5t, that's our u. Okay, so what we got here for our integral is we got the integral of 5 sine of 5t over u. So that denominator is just u now. So u is actually 4 minus cosine of 5t. And then plugging in for dt, what I have circled in blue there, we're going to be plugging in du over 5 sine of 5t. Okay, and the cool thing about my method is even though it's a little bit longer than the way they do it in the book, stuff just cancels out and it's kind of mindless, so it's hard to mess it up if you follow my method. Okay, so what we got here is we can see that the 5 sine of 5t's are going to cancel out. So just like the last problem, we end up with the integral of 1 over u du. Okay, so we have the integral of 1 over u du. Now remember, this one was actually a definite integral. I stopped writing the t equals 0 to t equals pi over 5. And the reason I stopped writing it is because right now we're in terms of u. So you can't have your numbers that you plug in originally in terms of t and then plug them in terms of u. If you did that, you'd have to change coordinates. So that's one way of doing it, but that's not usually the way I teach it. So the way I teach it is you do the integral first, and then you plug back in terms of your original variable, and then at the very end you plug in the numbers. Okay, so like here, the integral of 1 over u du is going to give us ln of absolute value of u, but we're not going to write plus c because this is actually a definite integral. We have to plug in the numbers at the end. Okay? So what do? Instead of writing ln of absolute value of u, we're going to go ahead and plug in what u is in terms of t. So we said that u was the same as 4 minus cosine of 5t. Okay? So we actually have ln of absolute value of 4 minus cosine of 5t. Okay, and now that it's back in terms of t, I can go ahead and plug in the original numbers they gave us. So the original numbers went from t equals 0 to t equals pi over 5. Okay, so we're going to be going from t equals 0 to t equals pi over 5. Okay, and just like before, when you have a definite integral and you have the numbers, you plug in the top number first, and then you subtract the whole thing evaluated at the bottom number. So this one's going to be a little bit more complicated to simplify, but we're going to go ahead and plug in. So we have ln of absolute value of 4 minus cosine of 5 times pi over 5. That's plugging in the top number. And then we subtract the entire function evaluated at the bottom number. So it's going to be minus ln of absolute value of 4 minus cosine of 5 times 0. Okay? Now we can simplify these a little bit. So the 5 times pi over 5 just ends up becoming pi because the 5's cancel. And then 5 times 0 is just 0. Now, if you don't remember your unit circle, you're welcome to use a calculator, even an online calculator. But I think I remember my unit circle well enough to do cosine. So cosine of pi is going to be the same as cosine of 180 degrees. So you're going to be on the negative x-axis. And cosine is the x-coordinate, so that's going to be negative 1. Okay, so cosine of pi is actually negative 1. Okay, so this whole thing right here is negative 1. Okay, and then cosine of 0 is going to be on the positive x-axis, and the x-coordinate there is going to be positive 1 on your unit circle. Okay, so this one, cosine of 0 is actually going to give us positive 1. Okay, so really, what we have here is ln of absolute value of 4 minus negative 1 minus ln of absolute value of 4 minus positive 1. Okay, and for the 4 minus negative 1, those minuses cancel out. So we get 4 plus 1 is 5. So we have ln of absolute value of 5. And then over here, 4 minus 1 is 3. So we have minus ln of absolute value of 3. Okay, and then we're almost done here. With this one, because 5 and 3 are already positive numbers, and absolute value is always positive, those numbers just stay the same. Okay, because absolute value is always positive, a positive number just remains positive. It's only if you have a negative number then it becomes positive. Right, so this is just going to be the same as ln of 5 minus ln of 3. Okay, and remember, when you're subtracting outside of a logarithm, that's the same as dividing inside the logarithm, and the order does matter. It's left to right, top to bottom. Okay, so this is going to be ln of 5 over 3. ln of 5 over 3. Pretty cool, huh? Okay. Now, I want to do a couple trickier problems. Okay, so the one we just did there was number 3. Oh. Alright, so let's take a look at problem number 4. Okay, so example number 4. This one is the integral from 1 to 7 of 2 ln of x all over x dx. The integral from 1 to 7 of 2 ln of x over x dx. Now this one's a little bit tricky. We do have a 1 over x here, but we can't just integrate it because we also have an ln of x. So as usual, when you have a complicated problem, you usually want to do u substitution. Now in this one, the ln of x is not a composite function, and neither is the 1 over x. But here you have to be clever about choosing u. So what we want to do is we want to choose u so that when I take the derivative of u, I get 1 over x. So it's kind of a tricky problem that way. So what we're going to do is we're going to let u equal ln of x. Now, how did I know to do that? I mean, ln of x is not a composite function. It's true. But why did I choose u to be ln of x? Well, because I knew that the derivative of ln of x is 1 over x, and I knew that that was going to cancel out with this 1 over x here. So it's kind of a trick. But once you know the trick, then the problem's not too bad. Okay, so du dx du dx is going to equal 1 over x. And I actually have it set up. I chose ln of x to be u because I remembered that the derivative of ln of x is 1 over x, and I knew that that would cancel out here. Okay, and then for our du dx, we can isolate dx. So to isolate dx, we multiply both sides by dx, and we multiply both sides by x. So this is going to become x du equals 1 times dx, which is dx. Okay, so x du equals dx. Alright, and then just like before, we're going to go ahead and replace dx with the x du. Okay, so we're going to plug in x du for dx. And remember, we said that ln of x is actually just u. So ln of x is u. So what we're going to be integrating here is a little different from the last problems. So here we're going to have the integral of 2u over x times x du. And this is going from 1 to 7. And remember, the 1 to 7, that makes it a definite integral. And because the original variable was x, that's actually going from x equals 1 to x equals 7. From x equals 1 to x equals 7. But because this variable over here is now u, I probably shouldn't be writing the numbers. So I'm going to go ahead and not write them there. Okay? And then we can see that these x's cancel out over here. So we're actually going to be doing the integral of 2u du. Now remember, when you're integrating, just like with derivatives, a constant times the variable doesn't matter. So you can bring the constant out front. So if I bring the 2 out front, then I have 2 times the integral of u du. And then what's the integral of u du? Well, remember, the integral of a variable, you add 1 to the exponent, and then you divide by the new exponent. So here, this is the same as u to the 1. Okay, so what we're going to do is we're going to use the power rule for integrals, which is the reverse of the power rule for derivatives. So we add 1 to the exponent, and we divide by the new exponent. Okay, so we're going to get 2. We're going to get 2 times u to the 2 divided by 2. So right there, we use the power rule. The integral of u to the 1 is u to the 2 over 2. Now this 2 in the numerator and the 2 in the denominator are going to cancel out. Alright, so we're going to be left with u squared. And then for the u squared, we can't plug in the x equals 7 and the x equals 1 because it needs to be in terms of x. Okay, so instead of writing u squared, we're going to go ahead and plug in the original expression for u in terms of x. So in this problem, the u that we chose was u equals ln of x. Okay, so since u equals ln of x, here we actually have ln of x quantity squared. And I put parentheses around the ln of x because when you square the whole u, that means you have to square the entire ln as well. Okay, so then we've done most of the problem now, but we still have to plug in the numbers at the end. So we have to plug in x equals 7 and x equals 1. Okay, so we're evaluating this from x equals 1 to x equals 7. Okay, and because it's a definite integral, we plug in the top number first, and then we subtract the function evaluated at the bottom number. Okay, so we're going to be plugging in 7 first. So we're going to have ln of 7 squared, and then we subtract that function evaluated at the bottom number. So that's going to be minus the quantity ln of 1 quantity squared. Okay? And then we can simplify this a little bit. I don't know if you remember this, but natural log or any logarithm of 1 is going to be 0. Because here e to the 0 is 1. So ln of 1 is going to be 0. Alright, so what we're going to have here is actually, we're going to have ln of 7 squared minus 0 squared. Okay? Ln of 7 squared minus 0 squared. But remember, 0 squared is just 0, so we don't need this. So our answer is going to be ln of 7 quantity squared. Now here's something a little bit strange that you might not know. For ln of 7 quantity squared, you're not actually allowed to bring the exponent out front. Now the reason you're not allowed to bring the exponent out front is the square actually doesn't refer to the 7, it refers to the entire logarithm. So that's an important little detail, but this is actually completely simplified. So just in parentheses here, I'll write, this doesn't mean, it does not mean ln of 7 squared. Okay? Because there's parentheses around the whole thing, you can't use the power rule for logarithms from pre-calculus, so you can't bring the 2 out front. Okay, so this is actually as simplified as it gets, and that's going to be our answer. So our answer is the quantity ln of 7 quantity squared. Okay? Alright, cool. So that was problem number 4. Right? Problem number 4. Yeah, so let's take a look at problem number 5. Okay, so example number 5. For example number 5, we have the integral from 0 to 2 pi over 3. The integral from 0 to 2 pi over 3 of 5 times tangent of x over 2 dx. 5 times tangent of x over 2 dx. Now for these, you can use the formula and you can use u substitution, but probably the easier way to do it is to use actually a new formula. So I'm going to teach you the new formula. I'm not going to prove it though, but basically if you write this as sine over cosine, and then you let cosine be u, and you do u substitution, you're going to wind up with this formula. Okay, so new formula. New formula. So it turns out, after you do u substitution, that the integral of tangent of u, is actually equal to ln of absolute value of secant of u plus c. Okay, I'm not going to prove this, but you could actually go through the steps. You would just write tangent as sine over cosine. You would let u equals cosine, and then you would do u substitution, you would integrate, and then you're going to wind up with this formula. Okay? But we're just going to use the formula because you'll be allowed to have it when you're taking the test or your quizzes and your homework. Okay? So, so using this formula, here we can see that our u is actually going to be x over 2. And this is the integral of tangent of u du. I forgot to write the du. Okay? So the integral of tangent of u du equals ln of absolute value of secant of u plus c. Of course, for this one, we're not going to have a plus c because this one has numbers. So we're going to be doing a definite integral here. Okay, but in this problem, our u is actually going to be x over 2. Okay, so u equals x over 2. And then taking the derivative of both sides, we get du dx equals 1/2. Because remember, the derivative of the variable x is just 1. And then we still have a 1/2 left over. Okay, so du dx equals 1/2. And then we go ahead and isolate dx. So to isolate dx here, we're going to go ahead and multiply both sides by 2 and also multiply both sides by dx. Okay, so we get 2 du equals dx. 2 du equals dx. And then we're going to go ahead and plug in 2 du in for dx in the original problem. All right, so what I'm trying to do here is I'm trying to get it in this form so that we can use our new formula. So the form needs to be integral of tangent of u du. And right now it's not quite in that form. So going back to our original integral, we can go ahead and bring the 5 out front because it's a constant. So if I bring the 5 out front, then what I'm going to have left is I'm going to have 5 times the integral of tangent of u, because remember, x over 2 we said was our u here. And then dx we're replacing with 2 du. So we're gonna have 5 times the integral of tangent of u times 2 du. Okay, so times 2 du. And once again, because the 2 is a constant, we can also bring that out front. Okay, so let's go ahead and bring the 2 out front, and 2 times 5 is 10. So here we have 10 times the integral of tangent of u du. 10 times the integral of tangent of u du. And now we can go ahead and use our new formula. This is just going to be natural log of absolute value of secant of u plus c. But we still have a 10 out front, so it's going to be 10 times natural log of absolute value of secant of u. But I'm not going to write a plus c. Now, why am I not going to write a plus c? Well, remember, you only write plus c if it's an indefinite integral. This one is actually a definite integral because we have numbers here. Okay? So the numbers that we started with were in terms of x, because the original variable was x. So this was going from x equals 0 to x equals 2 pi over 3. Okay? But right now, what we have here is 10 times natural log of absolute value of secant of u. Okay, so unfortunately, we still have to plug in the expression for u. So what was u? Well, we said u was x over 2. So we have to plug it back in terms of x before we plug in the numbers at the end. Okay, so we're going to have 10 times natural log of absolute value of secant of u, but we said u was x over 2. So we're going to go ahead and plug that in here. So we have secant of x over 2. Okay? And now that it's back in terms of the original variable x, we can actually go ahead and evaluate this integral from x equals 0 to x equals 2 pi over 3. Okay, so we're going from x equals 0 to x equals 2 pi over 3. All right, and as always, you plug in the top number first, and then you subtract the whole function evaluated at the bottom number. Now, I probably could have just left the 10 out front. In fact, I think I'm going to do that. So I'm going to go ahead and bring that 10 back out front. I didn't need to bring it on the inside. Because it's a constant, remember you can always factor out a constant from an integral. Okay, so what do we do now? We plug in. So plugging in, we've got a 10 out front, and then we have bracket ln of absolute value of secant of x over 2. So that's going to be 2 pi over 3 over 2. So that's plugging in the top number, which is 2 pi over 3. Okay, and then we subtract the whole function evaluated at the bottom number. So it's going to be minus ln of absolute value of secant of 0 over 2. Okay. And then we can cancel some stuff out. So to simplify this, remember if you have the same number on the top and the bottom here, these 2's are going to cancel out. So we're actually just going to have secant of pi over 3. Now remember that secant is the same as 1 over cosine. So if you want to type it into a calculator, you can rewrite this as 1 over cosine of pi over 3. Okay, so we have 10 times bracket, natural log, absolute value of 1 over cosine of pi over 3. Okay, minus natural log of, once again, we can rewrite the secant as 1 over cosine. So we can write it as 1 over cosine of 0 over 2. But of course, 0 over 2 is just 0. So we have 1 over cosine of 0 there. Okay? And then once again, either using a unit circle or a basic scientific calculator, you can simplify these. And just in case you don't remember your unit circle, I'll talk about it real quick. But most people should be familiar with the unit circle if they're in this class. From pre-calculus and trig. But with our unit circle, remember the common angles in the first quadrant. Common angles are pi over 6, pi over 4, and pi over 3. Okay, so this is pi over 6, pi over 4, and pi over 3. Okay, so this is just a quick review of the unit circle, just in case you don't remember this stuff. Okay, so in your first quadrant, this coordinate right here is going to be x is 1, y is 0. And then at pi over 6, we can see that x is actually larger than y. So for that one, we're going to have root 3 over 2, comma 1/2. So at pi over 6, it's root 3 over 2, comma 1/2. And then at pi over 4, let me zoom in so I can write it a little bit neater. At pi over 4, we have root 2 over 2, comma root 2 over 2. X and y are the same number. And then at pi over 3, x is smaller than y, so that one's actually going to be 1/2, comma root 3 over 2. Okay, so here's 0, pi over 6, pi over 4, pi over 3, and then up here is pi over 2. And at pi over 2, the coordinates are, well, x is going to be 0 and y is 1. Okay, so that's just a quick review of the unit circle. And remember, on the unit circle, it's in the form x comma y, but x is actually the same as cosine, and y is the same as sine. So these coordinates are actually in the form cosine of x, comma sine of x, or whatever your variable is, theta, x, t, whatever your variable is. Okay, but when you want to do something like cosine of pi over 3, if you don't want to use a calculator, you can just memorize the unit circle and use that. But for cosine of pi over 3, this right here is pi over 3, and we know that cosine is the first coordinate, so here cosine of pi over 3 is 1/2. Okay, but hopefully most people already knew how to do that from their other classes. Okay, so what we got here is 10 times natural log of absolute value of 1 over cosine of pi over 3 is going to be 1/2. Okay, and then we subtract natural log absolute value of 1 over cosine of 0. Well, remember, cosine of 0 is going to be the x-coordinate, which is 1. Okay? So we have 10 times natural log of absolute value of 1 over 1/2 minus natural log of 1 over 1. And 1 divided by 1/2 just flips it over. So we take the reciprocal. Okay, so we have 10 times the quantity ln of 2 minus ln of 1. And I went ahead and got rid of the absolute value because both of these numbers were already positive, so we didn't have to worry about that. Okay, and then remember that ln of 1 is actually 0 because e to the 0 is 1. Okay, so that's just 0. So at the end here, we're actually just going to have 10 times ln of 2. Okay, and technically you could move the 10 to the exponent, so you'd have ln of 2 to the 10th, but they don't do that. They just leave it as 10 ln of 2 because it's easier to read than some huge number. Okay, so 10 times ln of 2 is our answer. Okay. Now, there's one more problem in your homework that's quite similar to the one we just did. So I'm not going to be doing a full example of it, but I did want to write down the formula because one of your homework problems does have a slightly different formula than the one we just learned. So the new formula we learned here was for the integral of tangent. And again, I'm not going to prove it, but you can easily figure it out using U substitution. But there's another new formula. And I'm just going to write it down for you so that you can use it for your homework. But I'm not actually going to do a full problem because the full problem is basically the same thing as what we just did. It's just going to be as cotangent instead of tangent. Okay? So another new formula. So this one is for the integral of cotangent of u. So the integral of cotangent of u du actually turns out to be ln of absolute value of sine of u plus c. All right? So for another one of your homework problems, you're going to have to integrate cotangent, but all the steps are going to basically be the same as what we just did for this last problem. It's just you're going to be using a slightly different formula. Okay, so the integral of cotangent ends up being natural log of absolute value of sine of u plus c. Whereas for tangent, it was natural log of absolute value of secant of u plus c. But other than that, they're very similar, so I'm not going to do a full problem. So that'll be it for this topic. Thanks for watching.